So the reason I was talking about all of these expansions and calculating changes in energy and so on is because we want to look at systems like this. The example I showed you in the first lecture, this is the Stirling engine, remember? So I explained in that lecture, the bottom is hot. It's put on hot water, and the top is cold. So as this blue piston moves up and down, there is a change in temperature of the system, and therefore a change in pressure of the system, proportional to the temperature. And also you can see that this little black piston is moving up and down, and this is changing the volume of the system. Okay? So the system I'm talking about is the gas inside of this container. Right? There's gas inside here. So this blue piston moving up and down is changing the temperature of the gas, and this black piston moving up and down is changing the volume of the gas. And when the piston is up, it's a large volume. When it's down, it's a small volume. And it's clearly cyclical, right? It goes up and down and up and down. It does the same thing over and over again. Okay. So this is an example of a heat cycle, which, as I said, is the topic for the next couple of weeks. So I'll draw this big, because I want to explain a lot of things about it. We can plot then the behavior of this system on the pressure volume diagram. As I said, as the gas temperature changes, the pressure is changing. And also as the driving piston moves up and down, the volume is changing. So as the wheel goes around one revolution, the pressure and volume inside the gas change, well, something like this. Okay? I'm going to talk more about what shape it is later on, but it goes around in some sort of cycle. So it starts here. Let's say, well, it doesn't really matter where it starts. It starts somewhere, goes this way, goes that way. So you've got a system with pressure and volume as a function of time going in a cycle with some time period. Let's call the time period t. Okay. So as the wheel goes round and round, the pressure and the volume of the gas go round and round as well. Around here. Okay. So we can say some things about this. The temperature of the gas is changing. The temperature of the gas will be a maximum at some point around here. Okay. Temperature of the gas is a maximum somewhere there. And we can call this temperature TH, that's the hot or high temperature, the maximum temperature achieved by this system. And also, it will achieve its minimum temperature somewhere down here. So we can call this temperature TL, or low. Okay. So there are temperatures, this is a line of constant temperature, more or less, in the high temperature and the low temperature case. Okay. Now, as the gas goes this way, it is expanding, right? Volume, as it goes this way, is expanding. So that means it's pushing the piston up. So going this way, the gas is doing work. It's pushing the piston. Okay? Coming back this way, the piston is pushing the gas back down. Okay? So going this way, the gas is doing work. Going this way, work is being done to the gas. The gas is doing work this way from here to here, and then the piston is doing work on the gas from here to here. And we already said the work done was equal to the area under the curve. So the net energy, the net work generated by this cycle is given by the volume, the area inside the loop. So the area inside the loop here is the net work done. So from here to here, the gas is doing work. From here to there, work is being done on the gas. Okay. So to complete the picture, we also have heat. Heat is either going into the gas if it's being heated, or if it's coming out of the gas when the temperature of the gas is higher than the surroundings. So for example, in the Stirling engine you see here, when the blue piston is at the top, the gas is being heated by the water. When the blue piston is at the bottom, the gas is being cooled by the surrounding air. So heat is going in or out. And in this case, we can say that heat is going in from somewhere here to about somewhere here. So over this part of the cycle, heat is going in. And over the opposite part of the cycle, heat is going out. This red line is the heat going into gas, which I can call Q in, and the blue line is the heat going out, which I can call Q out. So that gives you a whole description of this system. Okay? It's being heated and cooled, it's expanding and contracting, and in the process, it's producing an amount of work equal to the area inside of this curve. Okay? There's one final important thing I have to define. Let me do it here. This is because it's on the quiz this week. There's something known as the efficiency. Which is given the symbol epsilon, and it's defined as the net work done in the system divided by the amount of heat you have to put in. So why do we define efficiency in this way? Well, imagine this is a machine. You want it to do work. Okay? You want it to produce as much energy as possible. That means you want this top work done to be as high as possible. Okay? Q in is the amount of heat you have to put into the system. So for example, in a steam engine, that's by burning coal. In a car, the heat is generated by combustion of gasoline, right, in the engine. So this is the amount of energy you have to produce in heat in order to make the thing work. Okay? So you want to make that as small as possible. The smaller Q in is, the less energy you have to give it to produce the same amount of work. So in a good engine, it should do a lot of work for a small amount of heat. That's a good engine, right? So a good engine will have a high efficiency, because this is a big number, this is a small number. Okay. But there's a limit on how efficient your system can be. The first law of thermodynamics, okay, so over one cycle, if I start and then go all the way around and come back again, over one cycle, it's obvious that the total change in internal energy of the system is zero, because you start and end in the same place. Right? So it must have the same energy. Now, in this case, the first law of thermodynamics will tell you that the change in energy, which is 0, is equal to the heat, which is Q in minus Q out, minus the work done, W, okay? And we assume that all of these are positive numbers. So that means that Q in must always be greater than W, right? Because this is positive. So if this equals 0, then this must be greater than that. And therefore, the efficiency, which is this divided by that, must be less than 1. Okay? So sorry to write down here, but it's just one more line. Therefore, the efficiency must always be less than 1. Because the efficiency is that divided by that. So in a good engine, you want this number epsilon to be as high as possible, but the maximum it can be is equal to 1. Okay. It can't be more than 1. Okay, I want to start off by talking about the Stirling engine, which I showed you a video of at the first lecture, and I've got the thing here. So this is an example of a heat cycle. And you see, I explained the operation is driven by these two pistons. There's this little black square here, which is moving up and down. This is called the drive piston. And there's the blue cylinder here, which is called the displacement piston. Okay. I'll just play that once more. Okay, maybe I'll draw it first. Okay, so the Stirling engine, I can draw something like this. Like this. So in here, you've got the drive piston, which is the black square, which moves up and down. And inside here, you've got the larger displacement piston, which is a big cylinder like this, which also moves up and down. Okay. So this one is called the drive piston. And this one is called the displacement piston. Okay. And they move up and down. Okay. Now, the volume of the system is the volume inside here. And that is controlled by the drive piston. If the drive piston moves up, then the total volume increases. If the drive piston moves down, then the total volume decreases. So the volume of the system is controlled by the drive piston. The temperature of the system is controlled by the displacement piston. So you remember that we keep the bottom hot. You put it on some coffee or something, and the top is cold. The displacement piston moves the air either onto the top, where it's cold, or onto the bottom, where it's hot. So the displacement piston controls the temperature, the drive piston controls the volume. Right. So I'll play this video again, and you notice that they are out of phase. The displacement piston goes up first, and then the drive piston goes up 90 degrees later, 90 degrees out of phase later. Okay? So that they follow each other like this. One goes up, and the other one goes up, one goes down, the other one goes down. Okay. So I can draw a graph of their positions then. So here I'm going to put position as a function of time t. And we'll call this displacement piston, I'm going to label as A. Okay. And the drive piston, I'm going to label as B. So if we suppose, first of all, that the displacement piston starts at the bottom, owing to the circular motion of the wheel, it undergoes a sine curve. So it will follow a curve which looks like this. So it's exactly, well, I've drawn it as an inverse cosine curve, but you get the point. Because it's a circular motion, it will go up and down in the sine curve. the displacement piston follows it slightly, the drive piston, B, follows it slightly behind. So the displacement piston goes up first, and then the drive piston goes up after it. So the position of the drive piston will look something like this. So this is the position of the drive piston B. So the change in volume of the system is exactly proportional to this position of the drive piston B, and the change in temperature of the system is determined by the position of A. When A is at the top, the system is hotter, and when A is at the bottom, the system is colder. Okay, right. Now I want to simplify this a bit so that we can draw a simplified, idealized diagram of it. So you notice here the position of the drive piston is nearly constant, right? Nearly constant. And the same up here, the position of the drive piston is nearly a constant. Okay. And in the other cases, the position of the displacement piston is nearly a constant here, and then here, and here. So I can divide this system into a number of stages which should all be of equal size if I've drawn it correctly, like this. And you see that roughly, approximately, in this first stage here, B is a constant. Sorry, let me write it in black. For this first stage here, B is a constant. Then for this next stage here, the position of A is a constant. Then the next stage here, again, B is a constant. And then in the final stage, again, A is a constant. Here, B is a constant. Here, A is a constant. Here, B is a constant. Here, A is a constant. Like this, right? Okay. So I want to draw a pressure volume diagram of this system now. So I'm going to divide it into these 4 stages like this. And in each stage, I'm going to assume that either the position of the drive piston is constant or the position of the displacement piston is constant. So I'll call this one stage 1, this one stage 2, this one stage 3, and this one stage 4. Okay. So first of all, what's happening in stage 1? In stage 1, B, that's the drive piston, is a constant. That means the volume is a constant. Because the position of the drive piston is a constant, the volume is a constant, roughly. Of course, it's not completely accurate. And the position of the displacement piston is going up. If the displacement piston goes up, that will force gas from the cold part to the hot part, and therefore the temperature will increase. Okay. So the volume is constant, and the temperature and the pressure are increasing. So on a PV diagram, that looks like this. You start out somewhere here. You have constant volume, and sorry, let me draw it a bit higher. You start out somewhere here. You have constant volume, and the pressure increases. So stage 1 looks something like that. In stage 2, the position of the displacement piston is at the top. Now that forces all of the gas in contact with the hot part, so we assume that temperature is approximately constant. The displacement piston is at the top. This forces all the gas to be in thermal equilibrium with the bottom plate, which is hot. Okay. So the temperature is constant, but the drive piston, that's this blue one, is moving up. And that causes the volume to increase. So the temperature is constant, but the volume is increasing. So if I draw that here, that gives you a graph which looks something like this. Okay. And remember, we had a word for the type of expansion where the temperature is constant. We called it isothermal. So this expansion here in stage 2 is approximately isothermal. Okay. So 3 and 4 just do the same thing in reverse, right? In 3, again, the volume is constant, but the displacement piston is now pushing the gas towards the cold part, the colder plate, the upper plate of the container. So therefore, the temperature and the pressure decrease. They go down. So that looks something like this. And then finally, I'm afraid I've got to write it on down here. Finally, again, the temperature is now cold, but it's constant. And the volume is decreasing. So the final stage 4 looks something like this. And both of these, number 2 and number 4, are both isothermal expansions, roughly. Okay. So we can make a cycle like this, and this cycle is indeed known as the idealized or the ideal Stirling cycle. So we can make up a Stirling cycle out of an increase in temperature at constant volume, then an isothermal expansion, then a decrease in temperature at constant volume, and then an isothermal compression. And that gives you a cycle which looks like this. Now, in fact, I've made some assumptions here. Right? The position of the cylinder is not really constant here and here. It moves a little bit. Also, the gas does not immediately reach the same temperature as the top or the cold. It takes some time for heat to transfer. So if you draw the real cycle of a real Stirling engine, it will in fact be somewhere in between this, right? So the real cycle will be somewhere in the middle of this, because the volume is never really constant, the temperature is never really constant, it's somewhere inside. But we can treat this black line as an idealized Stirling cycle, which will allow us to do some calculations, which we'll probably do in the next class, I think. I want to talk about 2 other examples of heat cycles today. The next one is known as the Rankine cycle, and this is very important for steam engines and steam power plants, which are very common these days. So this is a cycle where the gas used is water. Right? In this little model Stirling engine, we just use air inside here. But the Rankine cycle uses water, and there's a diagram of the cycle here, which again, you can divide into 4 ideal kind of stages. So you start off here with cold liquid water. It's pumped up to high pressure. So the pump increases the pressure of the water. So here you've got high pressure water. It then goes into the boiler, denoted by this fire here. That increases the temperature of the water, turns it into steam. So up here you've got very high temperature steam by the time you get to the top. You then use the steam to drive either a turbine or a piston to do the actual work, pushing the engine or whatever. Then finally, the steam, as it does work, the temperature drops. You collect it again in this thing known as a condenser, extract the heat out of it, and turn it back into liquid water. So one more time, as the water goes around this cycle, it starts off here as cold liquid water. It's pumped up to high pressure. It's heated to high temperature. does work in the piston or the turbine, it cools down in the condenser and turns back into liquid water. So this is known as the Rankine cycle. And we can draw an idealized version of it again, similar to the one we did for the Stirling engine. Okay. So I've done 4 stages there, 1, 2, 3, and 4. You start off in stage 1, you pump the water to high pressure. Okay? But because water is an incompressible liquid, even if you push a lot of pressure in it, its volume doesn't change very much. Right? It's nearly incompressible. So the pressure would increase a lot, but the pressure will increase a lot, but the volume of the liquid will stay constant. Okay, so you get a graph which looks like this. Okay. So that's stage 1 here. So if I write this in stage 1, the P increases because of the pump, and the volume is approximately constant because liquid water is nearly incompressible. In the second stage, you heat it up. In this part, it's inside the boiler, so the pressure is at a constant because it's all connected. So the pressure is approximately constant, but you increase the temperature, and as you increase the temperature, it expands, turns into a gas. So the second stage looks something like this. So in the second stage, the temperature and the volume increase. The pressure is approximately constant, and it goes from a liquid to a gas. And we said the term for that was vaporization, so the water vaporizes. Okay. In the next stage, it actually does work. And we should assume that this stage is quick when the steam is going through the turbine or the piston. So therefore, it does work without any transfer of heat. So we assume that the next stage is adiabatic. Okay. So stage 3, we assume, is an adiabatic expansion. So pressure decreases, volume increases, and the temperature goes down. Remember, adiabatic means Q equals 0, and therefore the temperature will decrease because it's doing work. And then in the final stage, again, it's approximately constant pressure, and you condense it back to liquid water. So in the final stage of the cycle, pressure is approximately constant, and the temperature and the volume decrease. P is approximately constant, and the steam turns back into a liquid, and we said this is called condensation. So the water condenses. So the liquid, it starts in a liquid somewhere around here. Okay? So between these 2 points, it's a liquid. So I draw a graph like this. On this side, we have liquid. And on this side, we have gas. Like that. So for this part of the cycle, it's a liquid. And for this part of the cycle, it's a gas. So there's one more very important cycle which I want to talk about, which is called the Carnot cycle. And this one, I'll just draw it. It's very simple. It combines two expansions and 2 compressions. First, you do an isothermal expansion. Then you do an adiabatic expansion. Remember, that has a higher gradient. Then you do exactly the opposite. So you do an isothermal compression and then an adiabatic compression. So you notice, because this is an isothermal expansion, the temperature along all of this point is constant. Let's call it TH, because it's high temperature. And the temperature along all of these points at the bottom is also a constant. Let's call it TL for low temperature. Okay. Now, the Carnot cycle is important for theoretical reasons because you can prove that it maximizes the efficiency of the heat engine. So if you want to know what's the maximum efficiency heat cycle, it looks like this. Okay. And we will prove this probably next week. Okay. So the Carnot cycle maximizes the efficiency of any cycle between the two temperatures, so between TL and TH. So if you change the temperature, then you change the possible efficiency. But between the fixed temperatures, the Carnot cycle always has maximum efficiency. And the efficiency of the Carnot cycle, we will prove next week, is equal to the difference in temperature divided by the maximum temperature. So given that we know that the Carnot cycle has maximum efficiency, you might ask, well, why don't we make every cycle look like the Carnot cycle? So why do we bother with steam engines, which have a cycle which looks like this, when they are always going to be less efficient than a Carnot cycle which looks like this? Okay? And the answer to this is practical. It's practically possible and quite straightforward to build an engine which has a heat cycle looking like this. But it's very difficult in practice to build an engine which has a heat cycle looking like this. So theoretically, this is the best. But practically, you always have to juggle trying to maximize the efficiency with coming up with a design which is possible to make, okay, make into a machine. Okay. So the Rankine cycle and the Stirling cycle, which I talked about first, are real cycles which you can actually build a machine for. The Carnot cycle is more theoretically important, and it's very difficult to build a real machine which uses the Carnot cycle. So before we finish, there's a few more slides on the presentation I want to show you. So in each of these cases, we need to get the work out of the system, right? So in this case, it's done here by, well, it says a turbine, or you can also use a piston. In the case of the little Stirling engine here, the work is done by pushing the drive piston up and down, which is turning this wheel. So I just want to show you some examples of how in practice this stage 3 works. In practice, how do you get the work out? Okay. So that's on the next slide of the diagram. Well, one of the simplest ways of doing it is using this thing called a reciprocating piston. So you have high temperature steam, for example, in a steam engine. And the high temperature steam can go in either side of this piston. So it can either go in this side when you see the arrow here, or it can go in this side when you see the arrow here. Okay? Now the side which is allowed steam to flow into is controlled by these valves. So these funnel-looking things here are valves. And well, the way they work is, you can see on the animation, so you have this axis along the top, like this, and it has these funny little shapes on it, like this, right? On the top. If you look at that end on, as it were, then you see the axis here, and they have, going around the axis, a shape which looks something like this, which is rotating, and then underneath it, you have the valve. So as this thing rotates, it will push the valve down and let the gas in, and then it will lift the valve up again and stop the gas. Okay? So as this thing goes around, the valve goes up and down. Okay. So that's what's shown on the top of this picture here. These are the valves which are being controlled by this axis here. Okay. So gas can go in from either side. When the gas is going in from this side, it pushes the piston the opposite direction, right? Because the gas is at high pressure. When gas is going in here, it pushes the piston that way. When gas is going in here, it pushes the piston the other way. So you alternate gas going in from this side, pushing the piston that way, then gas comes in from this side and pushes the piston that way, and you do it back and forth. Right? So you continually push the piston back and forth. And then finally, you need to have a space where the gas can go out, and that's this little bit here. So the gas goes in there, pushes the piston, and then escapes. It goes in the other side, pushes the piston, and then escapes. So it pushes the piston back and forth. Okay, so you can do it like that. You can make this more efficient by putting many pistons together. Okay? So what is shown here is just 3 times this. So this first unit is the same as this. It pushes the piston back and forth. But then the exhaust gas is fed into another, exactly the same machine, which pushes another piston up and down. And again, it's fed into another machine, which pushes another piston up and down. So in this way, you can increase the efficiency of the engine, because instead of just pushing 1 piston, it's pushing 3 pistons, all of which are powering the same machine here. So you can increase the efficiency in that way. Okay. Now this final diagram has quite a lot going on, so I'll explain it bit by bit. This is showing you the whole setup, okay? So the whole machine. So here, just this part, is the same as the reciprocating piston, which was shown on the previous diagram. So here you've got the valve, which is either letting gas in this side or in this side, and that's pushing the piston back and forth. The piston is being used to turn a big wheel in exactly the same way as the Stirling engine. The piston is used to turn a wheel. Okay. The motion of the wheel itself controls the valves. Okay. So both the valve and the piston are connected to this wheel, about 90 degrees out of phase again. So that ensures that the piston is always being pushed in the right direction. And then the final thing, which is quite interesting to explain, is this little spinning thing here. This is known as a governor, and the purpose of this is to control the rate of the steam engine. When early steam engines were first built, a big problem with them was that they were too powerful. So they would get out of control, they would go faster and faster and faster, and then it would break, okay, and you would have a disaster. So this is designed to stop that happening. And it's quite interesting the way it works, so I want to explain it. So the spinning of this is controlled by the spinning of this wheel. Okay? So the faster this wheel turns, the faster this governor turns as well. Now the governor is made up of a spinning axis which has 2 heavy balls mounted on it like this. Okay? So you can see the balls, one is there, one is there. Okay? So if the governor is at rest, then the weight of the balls just pushes them down to the ground. Okay? But as the governor starts to spin, there's a centrifugal force on the balls, and that will try and pull them out. Right? Exactly the same way as if you spin around, you feel a force pulling your arm out. Right? Now, the faster you spin, the higher and higher these balls will go, because the centrifugal force is getting stronger and stronger. And at some critical point, if the balls go too high, which means that the wheel is going too fast, it will turn off the supply of gas to the turbine. So if the wheel goes too fast, then the balls will raise, and the motion of the balls going up will pull this lever, which turns off the gas going into the turbine, and this shuts down the system. Okay? So this is a mechanical mechanism through which you can stop the engine if it's going out of control, if it's going too fast. Okay, so let's begin. Last class we were looking at examples of what are called heat engines. So we looked at 3 examples in particular, which were the Stirling engine, the Rankine cycle, which was what you find inside a steam engine, and the Carnot cycle, which I told you is the most efficient possible cycle of heat engine. And today I want to talk about a related topic, which is heat pumps. So first of all, I'm going to explain what the difference is between a heat engine and a heat pump. So a heat engine is a device which uses a difference of temperature and the transfer of heat from a hot place to a cold place in order to produce work. So schematically, we can draw it something like this. There's a hot reservoir at temperature T2. So we call this the high temperature reservoir. So this will be the steam inside a steam engine, for example. And then there's a low temperature reservoir, which in the steam engine is just the outside world at a lower temperature. And what the engine does is it uses the flow of heat from hot to cold in order to produce work. So again, schematically, we can draw this in the following way. Here's the heat coming out of there. It flows down to the low temperature reservoir. But some of the heat which flows out is able to be converted into useful work. So you can draw it something like this, okay? So there's an amount of heat, let's call it Q in, flows in from the high temperature reservoir, an amount of heat Q out flows down into the low temperature reservoir, and you produce an amount of work W per cycle, this is. Okay. So conservation of energy tells you that the heat that you get in should be equal to the amount of work you can do plus the heat that you throw out. And using this equation, we define the efficiency as the ratio of W to Q in, which must always be less than 1. Okay. So that's a schematic diagram of what a heat engine is. Now a heat pump is the same sort of thing except running backwards. So with a heat pump, an example of a heat pump is the air conditioning system. The heat pump takes heat out of a cold temperature reservoir, puts it into a high temperature reservoir, but in order to do this, it must expend a certain amount of energy. So it's the same cycle, but just reversed. So let me draw that. You have, again, the high temperature reservoir. This is the low temperature reservoir. But the cycle is reversed, so we take heat out of the low temperature reservoir and transfer it to the high temperature reservoir. But in order to do this, we have to spend a certain amount of energy. We have to do work. So the work now goes in rather than out. Okay? So we do an amount of work W, and a certain amount of heat is taken out of the low temperature reservoir, and a certain amount of heat goes into the high temperature reservoir. Okay. So it's the same cycle, but just reversed. An example of this is a refrigerator in a fridge. So in the case of a refrigerator, T1 would be the temperature inside the fridge. T2 is the temperature outside in the room. And what the heat pump inside the fridge does is take heat out of the fridge and put it into the room. And in order to do this, it takes a certain amount of electrical energy, which we call W. Okay. Now, similarly to the way we can define an efficiency for heat engines, you can define something similar for heat pumps, which is called the coefficient of performance. Coefficient of performance, and we can define it, let's give it the symbol C. What you want a heat pump to do is to take lots of heat out for a small amount of energy. Okay? So we define the coefficient of performance as Q out, the amount of heat you can transfer out per cycle, divided by the amount of work that you put in. Okay? So if C is a big number, that means it's a good efficient cycle. You take a lot of heat out for a small amount of work. Okay? But there's a difference between the efficiency of a heat engine and the coefficient of performance of a heat pump. In the case of a heat engine, you must have the efficiency as less than 1. Right? Because conservation of energy tells you that the work done must be less than the heat that went into the system. But in this case, you can, at least theoretically, have that the coefficient of performance is greater than 1. In other words, you take out more heat than you put in as work. Okay? Because conservation of energy only requires that Q out plus W equals Q in. It makes no condition on the ratio of Q out and W. Okay, so I want to explain briefly how heat pumps work, and in particular I'm going to explain how a fridge works. The principle is quite simple, and if you've ever pumped up a bike tire, you will know how it works. If you take a tire on a bike and you have to pump it up, then after you've pumped all the air into it, you will find that the valve, that's the point where you put the air in, becomes hot. So as you pump in the air, the valve becomes hot. You will also find that later on, if you let all of the air out of the tire, the valve will become cold. So these two facts, when you push gas into high pressure, it increases in temperature, and when you let it go from a high pressure place to a low pressure place, the temperature drops. Okay? This is known as the Joule-Thomson effect, and this is the basis of a refrigerator. So you can imagine it in this way. If I take a bike tire like this, and it's got a valve where you put the air in, right? So if I pump the air in, then this valve becomes hot. And if I let the air out, then this valve becomes cold. So if you want to make a heat pump, all you have to do is put 2 valves on, like this, and then you pump the air into this one gets hot, and then you let the air go out of this one becomes cold. Okay? Then, for example, if you want to make a fridge, you just put this single valve inside the fridge, so the fridge gets colder and colder, and this valve outside the fridge, so this gets hotter and hotter. Okay? In this way, you can transfer heat from here to here. Okay. Right, so this is the basic principle, but obviously it doesn't use normal air in the fridge because it's not very efficient. So let me explain in more detail how it works. Refrigerator. Let's go with that. Refrigerator. Okay, so this is a fridge, in other words. So I can explain how it works, and it is how I just explained, more or less. Here's your fridge. Fridge. Okay, and it's at some temperature T1. Okay, then outside the fridge, this is inside your room, and it's at a temperature T2. Now, in the back of the fridge, there's this heat pump. And there's this thing inside here, which I'll just draw like this, which is called a decompressor. And the job of the decompressor is exactly the same as the valve on a bicycle. The coolant comes into here at high pressure, and the decompressor lets it all out, reduces it down to low pressure. Okay, so the coolant will come in here and go down into low pressure. Okay. And in doing so, it becomes cool, it drops in temperature, and that's how it can take heat out of the fridge. So it comes in here at low pressure. Then outside the fridge on the other side, you have something which is doing exactly the opposite. This is called a compressor. Okay. And the compressor pumps up the pressure of the coolant to a high pressure. So the coolant flows in here, flows through here at a low pressure, goes into the compressor, and comes out at a high pressure, therefore high temperature, and then you have to lose that heat which you've generated through the compression process. So in order to do that, you use a series of pipes which go around the back of the fridge. Something like this. So again, the coolant comes in here, flows this way. So that's the general cycle. And if you look around the back of some fridges, particularly old fridges, you can actually see these metal bars around the back of the fridge. And if you touch them, they're hot. So this is where the hot coolant comes out and loses temperature to the air. Okay? The coolant is actually chosen, the chemical used is chosen, so that at room temperature and the high pressure it's at here, it will actually condense into a liquid. So at some point as it goes around this cycle, it will condense into a liquid. Then when it drops in pressure in the fridge, it will turn into a gas again. So at this point, the coolant condenses. So this is how a heat pump works in practice. Because of the drop in temperature when it goes through the decompressor, heat is taken out of the fridge. So this is Q out, the same as we drew here. And then when it goes through the compressor, it goes to high temperature, higher than room temperature. So heat is taken out of the gas there, as I've labeled it there. Okay. And the work done, W here, is what drives the decompressor and the compressor. Right? You have to do work to pump up the pressure of the gas here. Okay, so we can draw this cycle on a pressure volume diagram, as we did last time. I'm going to briefly do that and explain what happens in each stage. Okay, so let's label each stage. I'm going to start by, this is the simplest bit where the liquid is on the outside, so this is stage 1. Once it's gone through the compressor, until it goes into here. Then stage 2, I'm going to label the decompressor, where the pressure drops. Stage 3 is when it's inside the fridge, and stage 4 is the compression part of the cycle. Okay. So again, as an idealized system, we can write it in terms of 4 stages like this. So we start when it's just come out of the compressor. It's just come out of the compressor, so it's at a high temperature, and it's at a high pressure. So it's somewhere up here. So I need to make it somewhere here. Okay. Then, as it flows around here, it will cool down because heat is being taken out and going to the room. It does so at constant pressure, so it will move back something like this to a point somewhere here. So this is stage 1 of the cycle. Then in stage 2 of the cycle, this is the decompression part, so its pressure rapidly drops, and as it does so, it expands, so its volume increases, something like this. Then it's at low temperature and it's inside the fridge, so it absorbs temperature from the fridge at constant pressure, again like this. So this is stage 3. And the compressor pumps it back up to high pressure and high temperatures. So the compressor makes it go something like this. Okay. And again, as I said, it's liquid for part of this cycle. It condenses here, and then it vaporizes when it goes through the decompressor. So for some part of this cycle here, something like this, it's a liquid. So on this side, it's a liquid. On this side, it's a gas. Okay, before I do that, let me point out something obvious about this. The cycles we looked at last time, the arrows were going clockwise. If you look at the diagrams we do last time, the arrows are going clockwise. Whereas in this case, the arrow is going anti-clockwise. It's going in the opposite direction. That's because these cycles are doing work, whereas in this cycle, work is being done to the system. You're putting energy in. Okay, so that's why it goes in the opposite direction. So a cycle going in this way is acting as a heat pump. A cycle going this way clockwise is acting as a heat engine. Okay.